Hello, good morning, good afternoon. So let's continue with the part 3 of this module. So we have seen basic equation for AC, how we can compute power, voltage and current in some AC circuits. So let's see what happens when we have more than 3 phases. So before, remember, we created the idea of phasors, and phasor were understand as a complex number, but also can be interpreted like this rotating vector, which is projected, right? So it's projected on time, and then so you construct this kind of function. But we can actually use lines to not only transfer one voltage or current sinusoidal wave, but you can actually have two of them, and we can decide to generate them with some shifting. In this case, so this is 90 degrees. Well, you can also have here the representation. So let's say at time 0, you see how here the projection is this value, and at time 0 the projection is this value. As the time passes, so this is omega t is rotating, and this is t, so the projection are different. So we can have two of them in the same wire, or even we can have three of them, right? And this case is very, very, very interesting because, well, you see here we have three sinusoidal waves. So this is t here, and this is the value. So you see, like at time t equal to 0, well, there is one of those reference that they have 0, the other one is something positive, and the other one is something negative, which cancel out. But if we go to any other position, so we will see also that there are these three elements. So we have this, what is voltage will be 0 at this moment. The value of this one will be cancelled out with this one. So if we create three signals in such a way that they are shifted 120 degrees, so the sum of all of them at every moment is 0. And this actually have very important consequence. Let's assume like now we want to send energy from one city, here, Moscow, to another city. Here is St. Petersburg. Yes. Well, we need to create these transmission lines and create circuits, sending energy from one generator to one load. Well, we can build some circuits so where the source of voltage is connected to the line through one line which is sending energy, and the other one which is receiving. Well, actually it's not the truth, because like this is a sinusoidal wave, so current actually goes in one direction and then go into the direction a different moment. But basically like you need two cables. These have some real value and some imaginary parts. So there is some active power which is sent from this voltage source at Moscow to the St. Petersburg. Right. If we want to, let's say, to increase the power that we can send, so we can create, instead of one circuit, we can create three circuits, and we will have this green one feeding another load, and then we can create another circuit feeding the other load. We see like this is the three circuits. So those three circuits are what we call balance, and balance means C's are almost similar, almost equal. We are going to assume that they are equal, and voltage source also are equals. So if they are balanced, basically they are a copy of each of them, and then we are sending like 3 times P. We also can understand like how many cables we need from Moscow to St. Petersburg. In principle 2 cables times 3 circuits, so it means like 6 cable, which is long distance, and well, it naturally have some cost. What we are going to do is transform the circuit that we have here on the left to this circuit that we have here on the right. So again, this is basically the same impedance. I'm telling you that this is equivalent, and I will prove to you in a while. So we are connecting that, and we can remove the 3 wires. So at the end, so we will need only to have only three wires instead of 6 wires that we have in the left hand. So it means like when we have 3 phases, and I call phase to every of these circuits, when we have these 3 phases, we can reduce the amount of cables. We have some generator, can create these 3 signals. Typically it's only 1 generator, and they are representing these 3 signals by those phasors VA, VB, and BA, BB, and BC. They are typically use A, B, and C to define each of these phases. So we can say like, well, we have 1A like a reference in 0 degrees, and then we just need to shift 120 degrees. So there are 2 ways for shifting. So we can shift the second phase like lagging, and or it could be leading, right? So depends on if this is lagging or leading. So we call ABC sequence or ACV sequence. All right. Also, it's called positive sequence when it's this AVC, or negative sequence. You can see from here, like, well, for the positive sequence, like the phasor B is equal to, well, the same magnitude, because we are designing to be balanced. So all these 3 signals will be the same, and this is shifted 120 degrees. That is very nice, because at any moment when we are zooming up the voltage on these lines, so it will be summing up 0. So I have here I remember here these three phases. If I summing up the 3 of them, it will be 0. You can sum up these 3 vectors, and you see they are canceling out. If this is happening to this vector or this complex domain, so it's also happening in real time. I'm starting with a configuration which is Y, like those generators are connected in some kind of start, and loads also are connecting with some start. I will work with this configuration, and then what is called Wye-Wye. Source is Y and load is Y configuration. It is also possible to transform any Y configuration to delta. I'm finding what will be the equivalent of those deltas. It's better to go in the other way around. So if you have a generator which is connected in delta, or a load which is connected in delta configuration, so you are able to compute what will be the equivalent. There is not existing this Y source of voltage, but what will be the equivalent source of voltage that is in Y configuration. So anytime that you see any other configuration like this, so you can transform to the Y configuration. Let's mind that we have, again, this is my generator, which is in Moscow, for example, and this is St. Petersburg. They are far from each other, so I will need to use some transmission lines. So the first, but I'm doing like, well, these 3 source of voltage, they are connected in a common point, right? This common point is in here. I call N, and will be kind of a reference for me. So I will assume like this N actually is at the level of 0 voltage. Is my reference. Anything that I'm giving you in this circuit will be referred with regard to this N. For example, what is the voltage in this point? Well, the voltage in this point is B A prima N. So what is this is basically A prima. So is what is the voltage in A prima with regard to N? Yeah, what is the voltage on N is basically the drop of voltage in here. Then I'm assuming like what we have here on the left is a generator in this blue. And it's a kind of non-ideal generator that is composed with ideal generator plus some impedance, and this impedance is representing losses, resistive losses, also some other reactants, as you said with that, so something very general. Then we have between going outside of the generator, we have this transmission line. So actually from A to capital A, there is a very long distance, and I have some transmission lines, and this is representing the impedance of this particular line. Then I have here my loads on the St. Petersburg on the right hand side. So these three loads, CA, CV, and CC, are connected also in Y configuration. You see the three of them, they are connected in one configuration. So this is basically, this is A, this is B, and this is C. And then I say, well, I will compute, I will connect in somehow these three circuits by another line. This line is representing, let's say, these three lines that they are coming back from St. Petersburg to Moscow again. And then I want to compute, well, what should be the current that is going through this line. Okay, this is I0. And I can say, well, if this I0 is always 0, I don't need this line. Right? If this I0 in T is always 0, we don't need line for closing these circuits. If this IT is different than 0, so I will need to think about how big will be this line. So let's start with this Kirchhoff laws. So the current that arrives to this N, it will be this Bn, so this is the voltage that I have here with regard to this N, divided by, this is Bn, divided by C0. So this is basically I0. I will write this in a different way. This is equal to, and then I need to add here a minus, right? So with the minus in here also, this will be the current that goes from a small a to capital A. And you can see here, like, well, you have this, the voltage that you have here, I call BA prima N, minus the voltage that I have in this point. So this is all along to this path. Yeah, this is what is BA prima N minus Bn. Right? So the through this path in pink, I have three elements. The elements from the generator, the elements from the line, and the element from the load. So this is actually, I can compute what is the current of this element, and also the current for the case of B. So I have in this N, so I'm receiving I0, so it's leaving IAA. This is in this way IBB, and this is in this way also ICC. Right, so this is IBB, and this is ICC. Right, this is basically this balance at node N. Well, now let's assume the next thing. So we are going to assume that the system is balanced. And these actually have very nice properties, and electrical engineers are designing systems to be balanced because these have those properties that I just mentioned before, and then I will show here in a bit. So balance means, like, well, the three signals are balanced, so it means like they are 50, 120 degrees, right? BA, BB, and BC with the same magnitude. Balance also means that impedance of the non-ideal generator are the same. The transmission lines, the 3 wires, are also the same, so I designed the same. And the loads are the same. So I will connect in such a way that loads will be the same. I'm not giving you any restriction of the impedance at what we call neutral conductor. Neutral conductor is this one, the one that I'm using just to return from the C circuits. So C0 means like C0 can take any value. Well, I will call like CA generator A plus line from A plus the load. Well, I will call this all the impedance that I have in one phase, in particular the phase A. And this is the same for all of them. So if I'm replacing that, so I have this, yes, this relationship, the dependent C0 and C phi. That only can be possible if Bn is 0. So what is the mean of that? It means like, well, this value here, the voltage in here in N, must to be 0 when everything is balanced. And remember, B little n, it was 0 always. So it was my reference. So it means like between this point, this capital N and this little n, there are not voltage drop. So there is not any voltage drop. It means like no matter what is the impedance that I have in there, the current will be always 0. That is very nice. So we have no current through the lines, what is called neutral line, this one. And this is very interesting because I need, in theory, only 3 wires. So with 3 wires are okay, right? So this is one of the smarter things from power systems, and that is very cool. Okay, in reality, you can argue about, well, that is very complicated. How you can say, like in St. Petersburg, you will distribute the load. Let's say this is one area, this is another area, and this is another area of St. Petersburg. You will distribute the load in such a way they are always the same. This probably is not always the case. They are not accurate. Loads can vary a little bit, but even if they vary a little bit, so variation can be very small. So typically, this cable, this neutral cable, exists. But in general, I have to very small, very thin cable because it's just to compensate any unbalanced thing. In here, we are not going to deal with the unbalanced system, but there are some equations just to deal with that. Okay, then we can go also to the analysis of what happened with the currents. Remember, I've seen before what is the current. Well, basically, I represented here before what this is the current from A to A, well, with minus. And they are here again. So I can actually come back again to the definition of currents. From the current that goes through the phase A, it's equal to just the voltage that they have in this phase divided by the impedance of this phase. And for current in B is something similar, and from current in C is something similar. So that means like, well, I don't really need to know all the 3 phases. If I know my generator is creating 3 voltage sources that they are 120 degrees, right? This is 120, 120, 120, they are balanced. And the loads are balanced as well. So I can actually compute what is the value of one phase and then extend to the other ones, right? And you can see like, because this value is always the same for these 3 phases, if this is voltage in A, voltage in B, in voltage in phase C, you can imagine like the current in A will be shifted some value, whatever is the value, but it will keep this 120. That is because we are always divided by the same number. So this will be B, and this will be CC. whenever we have three phases systems, we can simplify this system to a single phase system. Just consider, for example, phase A. And this is typically what we are going to do. This is the way of we are going to analyze those systems. And we are basically taking just source voltage from A. There's some non-ideal elements, the main transmission lines, and this is the load. Once again, this is important to assume like everything is in Y connections. If this is not Y connection, so we need to transform some delta connection to Y connection.